Do you have any specific questions you'd like me to look at?
Yeah, so from our last meeting, we were on number 24.
Let me pull that out here. And let me change my share screen to the Elmo, which is not working. Oh, apparently it is. You can see my arm, correct?
Yeah.
Okay, so here we go. Number 24. Did you work it out?
I did. So,
And what did you get for your answers?
well, I got 47.829%.
47.829%, and then 52.171%.
Well, that was my question.
Well, you get this number by taking 100 and subtracting 47.829.
Yeah.
And you have to understand 100 is exact. It's defined.
So my specific question was, while working it out, I kind of lost track of which isotope was which.
Okay, well, it might help you to do this. Remember how we said X plus Y is equal to 1?
Yeah.
And I did something along the lines of this. The atomic weight is equal to the mass of 1 times the percent abundance of 1 over 100 plus the mass of 2 times the percentage of isotope 2 over 100. And right now I haven't defined which isotope is which, correct?
Yeah.
But when I start doing this, mass 1, if I write 150, I'm sorry, 0.9197, then here I'm talking about the isotope that has a mass of 151, correct?
Yeah.
Rounded off, it's 151. So I'm
Yeah.
talking about a europium 151 here, which is the same as europium 151. And here, if I write this U and then I write X, X is equal to the percent abundance of isotope 1 divided by 100. You have to understand that that's not aluminum. So I'll put a little dash there so you know it's not aluminum, okay? And then plus 152.9212 U times Y. So now that means that X is europium 151 and Y is europium 153.
Okay.
Now, let's see, do you know if you're right?
Nope.
Let's find out. So I'm going to do a change share to my browser. So you can see I have Zoom up here. I'm going to go to Web Elements. And I'm going to scroll down to europium. And I'm going to scroll down and see if I can find out the isotopes of europium. And here, you see it says abundances, but this doesn't talk about isotopes. It talks about in the universe, in humans and so forth. So I'm going to keep scrolling down. Uses, reactions, compound, binary, history, isotopes. So take a look here at the isotope pattern. The 151 has a percent abundance of 47.81, and the 153 has a percent abundance of 52.19. And didn't you say you got like 47 point something?
Yeah.
So you came out really close to what they have found experimentally.
Okay.
So good job.
Okay.
Okay. So I'm going to change my share back to my actual desktop, not my computer desktop. Any other questions?
I was hoping maybe we could go over moles, calculating, going between moles and AMU and atoms. That's where I'm at on the lecture. I haven't gotten quite through all the
Okay,
lectures, but I'm almost there.
so you want moles, atoms, and what was the other thing?
AMU.
AMUs. Okay. So here's some things to understand is that 1 mole is 6.022 times 10 to the 23rd. And I asked Chem 1A students to memorize this to 4 significant figures.
Okay.
Okay. And this 1 mole is equal to 6.022 times 10 to the 23rd is like saying 1 dozen is equal to 12.
Mm-hmm.
In other words, this doesn't have any unit like grams or anything like that to it. It's an amount.
Okay.
We also just figured out that 1 AMU or 1 U is 1.661 times 10 to the minus 24 grams. And you'll notice this doesn't have any labels. What I mean by that, it has units, the U or atomic mass unit, and it has grams, which is a mass, right? But no label. So this is used the same way as 1 pound is equal to 16 ounces. This doesn't have any labels. So here's what I mean. 1 pound of spaghetti is 16 ounces of spaghetti. Those are labels, spaghetti. 1 pound of tomatoes is equal to 16 ounces of tomatoes. Those are labels, tomatoes. So when I have something in addition to the unit describing what it is I'm talking about, that's a label. So what labels can we apply here? And the answer is anything. We could say 1 U of tomatoes is equal to 1.661 times 10 to the minus 24 grams of tomatoes. Now, normally when we use this, what are we referring to? We are referring to either atoms, specific isotopes, or molecules. Okay? And it's the same here. We don't have any labels. I could say 1 mole of tomatoes is 6.022 times 10 to the 23rd tomatoes. So those extra words we use are called labels. They usually refer in chemistry to the atom, or the, I should say in general, the substance, which could be an element or it could be a compound. So normally we use substances as labels. So we can convert between each of these if we want, because we know something about these. So let's say that we have 16.0, actually, I'm going to change this. Let's say that we have 52.1 grams of chlorine. Nope, not chlorine. What do I want to do? Copper. And we want to figure out how many moles and how many atoms. So we actually want to do 2 things here. And let's say that we have to use this conversion in our process. Okay.
Okay.
And I'm actually going to do this first, A, atoms. So I'm going to take my 52.1 grams of copper, and you can see above, I'm going to turn that into atomic mass units of copper. Now I'm going to write copper over here, and copper is number 29. And let's see what its mass is. 63.546. So that's the mass of one average copper atom. So I can turn this into atomic mass units, and then I can turn that into atoms. Because I can write this out as 63.546 U is equal to one copper atom. And I'm not going to write atom, let's say one copper.
Okay.
And I actually want to write 63.546 U copper is equal to one copper. So copper is my label.
Okay.
Are you with me there?
Yes.
So if I do this, I'm going to multiply by this up here, and I'm going to put the gram part on the bottom.
Mhm.
And I'm going to go ahead and use my label, copper, grams of copper. And then I'm going to put 1 U of copper.
Mhm.
So you can see the grams of copper cancel out. And then I'm going to go ahead and use this right here. And I'm going to put 63.546 U of copper per 1 copper. So the U's of copper cancel. Now, what should this number be compared to the amount of a mole, which is 6.022 times 10 to the 23rd? What should our number come out to here compared to a mole? Bigger than a mole or less than a mole?
Less than?
Less than, that's right, because you need 63.546 grams to get 1 mole. Now that's something you may remember from Chem 2. And here we only have 52 grams, so we don't have enough for a mole. So our answer should come out to be less than 6.022 times 10 to the 23rd. But you know what? 52 and 63 aren't that far apart. They're off by like 20%. So instead of 6, we want to get something that's like a 20% less than that. So maybe, let's see, 20% less would be 1.2. So maybe 4.8 times 10 to the 23rd is what we expect. Okay, so let's do the work. 52.1 divided by 1.661 second EE negative 24 divided by 63.546, and we get 3 significant figures because of that, right?
Yeah.
So I get 4.94 times 10 to the 23 coppers. Let me pause the recording for a moment. Someone just knocked at the door. Okay, so I think I said the answer should be like 4.8 times 10 to the 23rd, so not a bad estimate.
Okay.
Now, let's see how many moles of copper. So we can start off with this 4.94, but I'm going to start off with 4.936 times 10 to the 23. And I'm going to put my little arrow there saying that that's where I would round this if it were done. And I'm starting with, I'm not rounding early because you don't want to round early, right? And since this value is in my calculator, I can grab that 4.936 right off of it, right?
Yeah.
Now times here we're going to use our labels again. 1 mole of copper to 6.022 times 10 to the 23 coppers. So these cancel, and we know that this is less than 1 mole, so the answer should be about 0.8 mole. So let's see what we get. And indeed, I get 0.820 mole of copper. So that's how you would do all of that.
Okay.
Okay, so what I'm going to do here is I'm going to propose a different problem for you to do. And here's what I want you to do. Let's say that we have 0.152 mole of nickel. I want you to tell me how many nickel atoms that is. And then based on the amount of nickel atoms, I want you to then tell me how many what the atomic, I'm losing my words here. Sorry, I'm writing and talking at the same time, doesn't work well. I want you to first figure out how many nickel atoms, and then I want you to figure out the mass and AMUs of those nickel atoms. Okay, and then I want you to tell me the mass in grams of those nickel atoms in that order. And let me look up nickel for you. I believe it's number 28. It may be 30. It's 28. And it's 58.6934. And while you're working on that, I'm going to pause this and you're going to let me know when you're ready, okay?